Let's examine a crucial concept in calculus, instantaneous velocity. So what the heck is this? Instantaneous velocity. Instantaneous velocity is the velocity at a given instant. Now velocity is speed, but it could be forward for a positive direction or backward for a negative direction. Now, if we look at our traditional d equals rt equation, distance equals rate times time, we can solve this for r, and we get that rate is a function of, say, distance over time. Okay, so this is general. So typically what will happen is something like this. This is pre-calculus. You might be given a problem in which somebody travels something like 120 miles in 2 hours. And so what you can say, their velocity, their rate here is 60 miles an hour. Okay, so what's happening here, the 120 miles in, say, 2 hours is looking at a total distance over a total time. Okay, this is non-instantaneous velocity. This is what you would call average velocity. Okay, so velocity for the average, okay, AVE, equals what? It's a change in position, and we will typically represent position by x, over a change in time. And time, of course, is represented here by t. So note that triangle just means change, okay? So this, works for what's up here, where we have the 120 miles, go from 0 to 120, go from 0 to 2 in time, okay? So average velocity is basically a concept that has been with us for a while. Instantaneous velocity is more, you could say, recent. So Zeno argued that it's impossible because an object must be either at rest or in motion, and at a given instant. And if at a given instant an object is in motion, then there must be some kind of a duration of time which you can then subdivide further. So he used this to argue that therefore it can't be in motion, it has to be at rest. And if an object is always at rest, it simply cannot move. Okay, this is a logical argument that we know doesn't hold up in reality. But the question of what's your velocity at a given instant, it seems almost impossible, and it actually is equivalent to the tangent problem that we introduced at the very beginning. So how do we move forward to figure out instantaneous velocity? Let me just write it up in terms of limits. So if we look at v by itself, how do we transform the right side to not get the average but the instant? Okay, there's an idea with limits. And so, imagine that you're in the car and you're driving and you don't have a speedometer, but you want to know, well, how fast am I going at this instant? If you look at the distance you travel from point A to point B over the smaller and smaller time intervals, if you collapse that time interval to 0, okay, so you take the limit as delta t goes to 0 of delta x delta t. That is basically a definition that works for instantaneous velocity. Now, what happened in actual practice? Okay, so in actual practice, we've got Galileo, okay? Galileo comes along and does experiments trying to figure out what happens with falling objects. Okay, now from Galileo, the basis of his work, you can arrive at an equation, say, s equals 4.9 t squared. Now here, s is actually the distance. And, here I said, distance is x, and now here I'm saying s. Okay, I could do x again. S is also used, it's used in a lot of textbooks. It doesn't really matter. I guess the idea here is that if you're graphing it, and you call this t, students are used to that as the x-axis and can get confused, so sometimes s is given as position. Okay, so this basically is attributed to falling objects. Okay, you can use this equation to figure out where they will be at a given time if you drop them. Okay, and we know what this looks like. It's going to be the right side of a very steep parabola. And we've done basically a problem just like this. So what's important here is the interpretation. And the interpretation is that what instantaneous velocity means, if you take a given instant of time, pick some value of t, and you want to know, hey, what's the instantaneous velocity at this time? Well, you've got a tangent line that basically gives you the instantaneous velocity at that time. Okay? So the resolution of this then is just like what we've done before. Okay? It is figuring out, we had the limit as, now there are different ways you can write it. We'll just do the classic one. Limit as h goes to 0 of f of x plus h minus f of x all over h. So this has been given as the definition of the derivative, which will deliver the instantaneous velocity. Okay, so this is interesting. Why don't we go ahead and do this with this particular equation, and let's see what we in fact get. Okay, so the function is 4.9 t squared. Okay, so in effect it's a function of t here, not of x, and so we can modify it accordingly. The variables can interchange, of course, what they stand for, and so if you like, we could say limit as h approaches 0 of f of t plus h minus f of t all over h, since we're looking at t, as our variable here. Okay, so how do we do this? Well, we know how to do this, right? It's 4.9, and then whenever we see a t, you put in t plus h squared minus 4.9 t squared all over h, limit as h goes to 0. Okay, but you can pull out the 4.9. Limits distribute, okay? The limit of a constant times something is the same as that constant times the limit of the terms. Okay, so if you pull out the 4.9, you don't have to, you could leave it. You end up with 4.9 limit as h goes to 0 of t plus h squared minus t squared all over h. And we've done that before, okay? You could multiply it out, you could cancel the h, and what will you be left with? You'll be left with 2 times the variable. Okay, so what we end up with, okay, when we're doing this, we end up with the following. We're going to get 4.9 times 2t. But now in this particular problem, this represents the instantaneous velocity. Okay? It gives you the velocity of an object that is falling at any given time. And so we get v equals 9.8 t. Okay? Now, we can do this again. Okay? We can say, all right, so we figured out the velocity. What about the acceleration? Okay, what's the acceleration? Okay, like over here, the acceleration, okay, just say A average, is the change in velocity over the change in time. Okay? That's what acceleration means. It's how fast your speed is changing over time. So acceleration then by definition will be the limit as delta t goes to 0, and in both cases delta t goes to 0, of delta v over delta t. Okay, and once again, it is the rate of change of, say, the velocity to time. And the way that you do that is you compute another derivative. Okay, so what I'm going to do now is plot this one, this v equals 9.8t, and if I plot this, get the following. It's simply a straight line that goes, but at a steep slope, a 9.8, slope. And so the question of what is the derivative of this function, what is the slope everywhere of this function? Well, it's clearly 9.8, okay? So acceleration is 9.8, and you may know that as the acceleration of the gravitational field of the Earth. It's 9.8 if you want to put in units, meters per second squared. The reason why seconds are squared here is because you're doing it twice. There's two delta t's here. So this is super interesting, and it's very profound. So let's just highlight now a couple of things here. Okay, so what we have is that, let's make a little summary here. Okay, we've got that S is position. Okay, and so if S is position, what is V? Okay, well, velocity is equal to, I'm going to use a kind of notation here, S prime. Okay, this is very similar to Newton's notation, which had a dot on top of it. And that means it's the first derivative of position, right? You start with 4.9t squared, you take the derivative, you get 9.8t for the velocity. Now acceleration is the derivative of velocity, okay? Right, we have our 9.8t, we take the derivative and we get 9.8. But what's interesting is we started with position. And so you can also say that acceleration is the second derivative of velocity, okay? You'll see some different notations for derivatives. The prime, one prime means one derivative, two primes means two derivatives. This is due to Newton, okay? And don't underestimate like the power of some of this stuff, right? So Newton comes up with this when he's writing his great Principia, and one of the big questions, you've got planets going in orbit, elliptical orbits around the sun, and so if you have a planet that's, say, here, okay, it has an acceleration, it's due to the gravitational field of the sun, and at any given instant, if that sun were to disappear, what would happen? The planet would go off on its tangent line. Okay, and so the tangent line, as we know, is the derivative here of the position. Okay, so one other thing I just want to address is this application is looking at position over time and how objects are moving in position over time. But sort of the arguments presented, we have an equation, we have a curve, we have a time axis, could be anything over time. And this is why calculus is so powerful, because it's not just an application for position over time to get velocity and acceleration. Okay, you can derive, by the way, Newton's laws from calculus, laws of motion. It works for anything over time. So it could be like the changes of chemicals over time for chemistry. It could be representing the change of economic markets over time for economics. This is why calculus is so powerful. Things are changing, and many of the sciences study how things change, right? If nothing ever changed, it would only be so interesting. People used to think things like, oh, the stars don't change. Oh yeah, they definitely change. Astronomy, physics, calculus is the language of these subjects because they are studying how things change over time. And that is one of the most powerful applications that you will find of calculus, both for velocity and acceleration, specifically in regard to kinematics, which is the study of motion, and also broadly, how do things change over time.